So welcome back everyone for today's session of the Cardiff Analysis Seminar. Today we are delighted to have Matteo Novaga from the University of Pisa, who will talk about non-local evolutions of convex and min-convex sets. So please, the floor is yours.
Okay, so thank you very much for the invitation to this telematic conference. Hopefully we will be able at some point to meet again and to have a normal talks. Okay, so in this seminar, I want just to resume to describe a few results I obtained in three papers in the last few years, which are with these people here, which are mostly Italians, Chambol, Buffini, Di Piero, Cesaroni, Valdinocci, even if they are not, well, Chambol is not, he's in Paris, and now in Dauphine, he's in Bologna, in Padova, and these are in Western Australia now, so but they are Italian. And the argument is just to try to study evolution by some, let's say, non-local mean curvature, so some non-local geometric evolution equation, and trying to isolate some geometric features which are sort of quite general, so do not depend on the specific evolution we consider, but they are, let's say, shared by a class of evolutions. Okay, so in particular, let me describe what is the evolution equation we will consider. So the evolution law. The evolution law is, as usual, we have some surface, hypersurface in Rn, and as usual for geometric problems, one prescribes the normal velocity. Let's call it, let's say, v, the normal velocity v, and the normal velocity v will be equal to an object which is called the non-local mean curvature, which is defined through an integral. So that's the equation. This is defined through an integral, and it's hk of x is the integral in, let's say, in Rn. Here we are, sigma is my evolving set, is a subset of Rn. The integral of, so sigma, let's say sigma is a boundary of an interior set, and here we have this set E is an Rn. So I take sigma, the boundary of E, I integrate a suitable kernel outside of the set and make the difference with the integral inside the set. So I have a kernel, which is k of x minus y. I integrate the kernel centered in the point x outside. So outside means I multiply by the characteristic function of the complementary, and I take out the integral of the kernel inside. So it's a difference. Now I write in this way only because I want to be a little bit more general. Of course, I could have written this as the integral of k on the complementary minus the integral of k over E. Let me write in this way because I want to allow that k satisfies where k satisfies some properties which are basically, okay, I want a positive kernel. This because I want somehow that this problem is, let's say, well posed in the parabolic sense, which means I want that this problem easily satisfies a comparison principle, because I want it's a second order. This one is a second order equation, like the heat equation, only it's geometric. So the main feature I want is a comparison principle. The comparison principle, okay, is reflected in the assumption k positive. So this is for comparison principle. This is for comparison, which is something. Comparison also means well-posedness of the equation. Then I want symmetry. I want symmetry because I don't want to distinguish the evolution of a set by the evolution of the complementary of the set. I want that everything depends on the boundary. And so there is a symmetry assumption, which is satisfied in most of the examples where typically the kernel is even radial. So radial in particular implies this symmetry here, symmetry with respect to the origin. And the reason of the symmetry is because then I have to distinguish, then as I said, the evolution of a set is different from the evolution of its complementary, which is sort of unusual, strange. And then there is an integrability condition, because essentially I want that this mean curvature makes sense. So if I compute it, I don't know, on a sphere, I want to pick up a number, like not plus infinity possibly or something like that. And so there is an integrability condition, which is that the mean, that the integral of the minimum between this and this, k of x less than plus infinity. Okay, of course, if k is in L1, which means the integral of k finite, this has perfect sense, because I integrate the kernel on the complementary minus the integral of it. Here I'm just saying that I can allow kernels which are a little bit more general than L1, and still, since there is a difference here, this integral makes sense in a sort of generalized sense, because of course this integrand here is not L1, but so I have to take out, you have to define the mean curvature in the, how do you say, improper singular integral. So you take out a little ball, you take the limit as the little ball goes to 0, and under this assumption here, which is a little bit more general, it makes sense. And for example, every C infinity set has a well-defined mean curvature, which is something which I want. So I can allow little singularity. Let me just make an example why there is this singularity allowed. So we go a little beyond the L1, because the typical example which has been studied in the recent years is the fractional mean curvature. And of course, it's the mean curvature where the kernel k is equal, k of x is equal 1 over x to the n plus s. S. Sometimes it's 2s, s is not s in 0, 1. This has been introduced by Caffarelli, Rock-Joffre, Sabin. Well, let's say it was Rock-Joffre. It was already introduced in some sense for functionals on function, but in the geometric sense, the study of this object and the parallel with the usual mean curvature, so the geometric analysis, in particular from the point of view of calculus of variation, has been started by Caffarelli, Rock-Joffre, Sabin, and then then several authors, mostly of the group of Caffarelli, among which Di Piero and Baldinocci in particular, which I mentioned before, studied several properties of the stationary problem and the evolutionary problem. So in this case, as you see, the kernel is not in L1. This kernel, that's why I asked that more general. But other examples which have some physical interest, another example is, let's say another example, for example, in R3, it's a kernel given by and this kernel here corresponds to some screened Coulomb energy. Is it true that for this screened Coulomb energy here, let's say it's more natural if I consider this kernel here to study variational problems, stationary problems, more than evolutions. But I just want to give you a couple of examples of kernel which satisfy the equation. As a remark, the equation V equal hk in complete analogy with the mean curvature flow, which is a gradient flow of the area function. Also, this equation is a gradient flow. It's a L2 gradient flow where, of course, when I write L2 gradient flow, it means, well, we are not in L2. We consider characteristic functions, and so it's a usual geometric L2 gradient flow. When you do the first variation of an energy defined on sets with respect to, there is a suitable notion. Now, I don't want to enter in the specifying the first variation, but it's a gradient flow of a non-local perimeter. Non-local perimeter pk of E, which is the interaction between E and the complementary of E through the kernel. Okay, so that in some sense there is an analogy. There is an analogy between perimeter and mean curvature flow, non-local perimeter, non-local mean curvature flow. The difference is, of course, that while the perimeter lives only on the boundary of a set, this non-local perimeter is a sort of a volume, is more similar to a volume term in some sense, because you integrate inside and outside, and it's non-local in some sense. But there is an analogy. So, okay, so properties of the evolution, properties, general properties. Well, let's say existence and uniqueness. And uniqueness. This problem has been discussed, and let's say, first of all, let me just state two results. One result is, as usual, one want to follow the analysis which has been done for mean curvature flow. Mean curvature flow has two, let's say, two main ways of attacking, of studying the equation, which is to consider smooth evolution, C infinity evolution, and to study properties of that C infinity evolution. In particular, evolution of geometric quantities and maybe singularity formation. Second approach is to, by some approximation method, to be able to define global weak evolution, which are less regular, of course, much less regular. They go through singularities and then study some property of the weak evolution. So there is the smooth world and the weak world, somehow the strong. Okay, so in this sense, I want to mention two results in the non-local case. The first result is short time existence, short time existence of smooth evolutions. And this is done only for the kernel, and this is done only for the kernel k equal 1 over more, the fractional kernel. And in this case, there is a work by Yulin Lamanna saying that if you start from a, well, the initial set can be C11, but if you start from a smooth set, for short time, you have a smooth evolution. And then in this case, there is also the evolution of geometric quantities. Such as, for example, hk, which is this type of properties, has been studied for smooth evolution. The computation of the equation satisfied by geometric quantities has been discussed by Saetz and Baldinocci, under the assumption that you have a smooth evolution. Now, in this work, in this talk, I want to focus mostly on the other approach, which is the approach of weak solutions. Now, for the weak solutions, there is one main notion, and then you have here global existence of weak, let me write viscosity, because weak solutions, they come in several, there are several ways to pick up weak solutions. The main one, well, I will discuss, maybe I will present two, but the main one is a viscosity solution. Let me just very briefly say what I'm talking about. And viscosity of weak solutions. What do I mean? I mean the following. First of all, I transform the geometric equation into a parabolic equation in Rn by the so-called level set formulation. Level set formulation is the following. I want to pick up the equation, I want to pick up an equation such that, for a function u, such that each level set geometrically evolves with my geometric evolution law. So this, from a geometric evolution law, I look for that parabolic equation, and which is the following: ut equal the gradient of u, and then I have hk, and here I have to decide if I take sub-level set or super level set, is not so important, u greater of u of x. That's a set, and this is required for xt in Rn times 0, 0 t plus infinity. I don't know. Okay, this means that each level set of u evolves by velocity equal hk. So that's my equation. It's a non-local equation because you see there is an operator here. There is an operator here which in fact is defined through an integral. So it's a parabolic equation, but it's an integral differential equation, this one. Okay, and also, as you can see from here, it's degenerate when the gradient is equal to 0. So it's a little degenerate. It's a integral differential equation degenerate when the gradient is 0, but formally at least satisfies the maximum principle, which is what is needed in order to apply the usual viscosity theory. So there exists, so there is a theorem, if you want, that if u0 is uniformly continuous, then there exists a unique u, which is continuous. Let's make now n times 0 plus infinity. Solution in the viscosity sense. Now, of course, here I should say, what does it mean to be a solution in the viscosity sense? Okay, if U is regular, it means to be a solution, satisfies the equation pointwise. If U is not regular, as usual, I don't want to enter this viscosity theory, you have to take some smooth test above or below, use the fact that the operator satisfies a comparison to pick up an inequality and say for each test touching from above or below, there is a certain inequality satisfied. Okay, I don't want to enter, but it's a way to use a comparison principle to be able to formulate a notion of solution which is more general. You see here we have continuity, so in general it's not even clear. The equation does not make sense. You cannot even differentiate this. Okay. Typically, okay. So as a remark, typically U0, for example, you need the distance. It's a sine distance function from the set E. Sine distance. That's a possible typical, so you have the set E. And I have that E, that's U0. Okay, so I pick up a function for which the zero level set is U, and then I can define E plus of T as U greater or equal than T, my solution, E minus of T equal U greater than T. These, of course, are contained, and these are this one are the maximal and minimal viscosity geometric solutions, viscosity solution. Starting from E. Okay, so the viscosity, okay, first of all, let me just tell you who proved this result. It was proved by Cyril Lambert in the case of the fractional operator, when K is that operator, and in general by Chambol, Morini, e Ponsiglione. This is more general and includes all this evolution equation and even more general equation. Okay. As a little remark, the uniqueness for the solution U does not imply uniqueness of the geometric solution, because the solution is unique only what I'm saying here is, of course, the same for the usual mean curvature flow. I'm just extending, but up to now, the theory, of course, the proofs are different, but the theory is exactly the same. So the solution is unique, is geometrically unique, if essentially, well, if E plus minus E minus of T, which is a level set U equal T, is equal to 0, for example, in measure. If we have this, that the level set of T has 0 measure, we say that the solution is unique, otherwise it's not unique. And otherwise, there is the so-called, there is what is usually called fattening, which means that at some point the solutions E plus and E minus sort of decouple. Typically, when they decouple, they don't come back right away. They stay separated. There is a bifurcation. So typically what happens at some point, there could be a singularity out of which you flow in different ways. So if you flow in different ways, there is geometric non-uniqueness. This does not contradict the uniqueness up here. It's just a geometric non-uniqueness because you find a singularity from which you can split in different ways. Okay, now just to complete about the weak solutions, I want also to tell you about another possible way to construct a solution, which is what usually is called minimizing movements. That's a technique to construct, it's a technique to construct weak solutions, such as the viscosity solution before. It's not the only technique, because the viscosity solution typically is constructed in an abstract way as supremum, for example, supremum of all the regular subsolutions by Perron method. And that's a typical way, a little bit implicit maybe, but a typical way to construct a viscosity solution, or infimum of all the regular supersolution. But there is a variational method to construct the solution, which is interesting in itself, and I want to, sometimes is useful to prove something, so I want to also to describe. And this was introduced by Almgren, Taylor, and Wong for the mean curvature flow, and also independent, a little later, but independent by Luckhaus and Sturzenegger. Luckhaus and okay, just Sturzenegger, and which amounts it's a time discretization. You fix a parameter positive h, which is a short time, and then you construct by iteration h n plus 1 is the argmin of the following energy, pk of E plus, and then you integrate on E the distance, well, maybe there is a minus if I define it this way, minus the distance, the sign distance function from the set En. And in this way, and you start from E0 equal E, and so you essentially you want to, it's a Newton method if you want. This one is like Newton steepest descent, Newton method. So in this way you can construct, of course it's not unique, because in general it's not unique, because as you see here, this problem here can have more than one minimizer, but okay, you have a way, maybe you can select some minimizer, but let's say in general it's not unique, and you can construct in this way EH of t equal EH by piecewise constant jumping at each time it jumps, so t over h integer part. That's a discrete evolution. And then in general, this will converge. You need some compactness, but this will converge to some E of t, weak solution. And notice that automatically, since you minimize the perimeter with the penalization, automatically you have that the perimeter of each EH, and then also of my limit with solution, is decreasing. Okay, so a general result, which is known in this case, is that for the limit EH, we have that it's always contained between the maximal and the minimal viscosity solution. In particular, in case of geometric uniqueness, in the non-fattening case, there is equality. Oh, this also was proved, this property here, in the paper which I mentioned, Chambol, Morini, Ponsiglione. Now, what we wanted to study is the properties of the evolution of some geometric quantities. So what about if we consider some specific class? Now we want to look in the evolution some special case. Maybe let me just point out as a remark, a couple of open questions here, which are not completely clear. One is the following. But it's not a remark, it's an open question about this limit, open question, open problem. The map which goes from T to the volume of EOT is continuous, so there are jumps or not. This is true, okay, for classical perimeter. And this was proved, for example, in the paper I mentioned, in the two papers I mentioned, Almeida-Lewong, Lukaus-Tutenek, this was proved. But in the general non-local case, is more complicated, and at least I never. There are some technical difficulties, classical perimeter. And second question, which I think are two questions of some interest, the limit. Does the limit satisfy the equation in some sense? Because, I mean, okay, the limit does satisfy an inclusion with two sets, and these two sets, E plus and E minus, they do satisfy an equation in the viscosity sense. So in some sense, also the limit. But for example, it could be different in case of fattening. So does the limit satisfy some equation? In some sense, some equation. In the classical case, this was part of the paper of Lukaus and Sturzenegger. They showed that the limit satisfied the evolution equation in a suitable distributional sense. So the limit should satisfy the limit equation in a suitable distributional sense, but this has not been. This question has not been really probably considered. Now, let me just proceed, and I want to look to some special classes. Of sets. The first one is convex sets. Now, for the convex sets, one can show, and this is in fact interesting in some sense, that E plus of t, so first of all, E plus of t is always equal to E minus of t. Well, let's say closed, because one is closed, the other is open. There is always, and they are always decreasing. The E plus of T1 is contained in E minus of T2. Well, maybe there is a closure here. Let's say maybe there could be some closure here. If for every T1 greater than T2. So they coincide, they are the same set up to closure, and they are decreasing. So everything in particular is contained in my original convex set. So what's happening is that if I have an original convex set, then I have my evolutions, which are one inside the other. E plus and E minus are the same, and they're one inside the other. And also, what is interesting is that E plus of t or E minus is the same, plus minus are convex. Now, this is proved only in one case, so let me just say. Maybe I should. This is only for K for all T. So the convex sets for the non-local evolution are maintain the property of being convex, and you never have fattening, so there is geometric uniqueness, and there is a fibration of convex sets inside your initial data. Now here, unfortunately, I would say this was part of this paper which I mentioned by Chambol, myself, and Ruffini. Only in this specific case, and the proof is not satisfactory, I would say. So the remark, proof not satisfactory, because we use a sort of trick to prove this result. And this result about convexity is a result. How would you prove this result? I would say normally, would you try to in two ways. The first is looking at the PDE in viscosity sense, and showing, for example, that for that PDE in viscosity sense, which I mentioned at the beginning, ut equal gradient u hk, if I have a convex function, then the solution remains convex, for example, for all time. So the PDE preserves convexity. That would be one way, but we were not able to do this. And another way would be, okay, look to the minimizing movement scheme, which I mentioned one moment before, and show there that if I have a convex set, the minimizer at one step preserves convexity. Also, we were not able to do also this one, the second one. So we used a third approximation of the viscosity solution. Another approximation of the viscosity solution I don't want to enter is what is usually called for the heat, how do you say? It's an approximation by convolution. Let's say you sort of linearize the equation, and you do a little shot of the linearized equation, then you restart, and then you iterate that. How do you say heat? I don't remember how do you call normally this type of approximation, but it's a thresholding scheme. Is a thresholding convolution scheme. And with that scheme, using some property of the convolution with a specific kernel, which we were able to prove that convexity was preserved. But it's quite specific. And that's why our proof essentially is restricted to this specific type of kernels. On the other hand, I have the impression that this result of convexity preserving could hold more generally with proofs which are more, let's say, in the viscosity theory, using the techniques of viscosity theory. But we were not able to do it. So for the moment, we have only this result here. And
sorry, can I ask a question, please?
Yes.
So this second line you have E plus T1 container sign E minus T2. Why is that not true? Is that true in general, even if you take a different kernel? Just
your question is if this is true even for a different kernel?
Yeah, because unless I wrote it down wrong, is E plus the set of points where U is bigger than or equal to T, and then E minus where it's strictly bigger than T.
Yes, but here you are taking different. So this in general is. So this you're asking about this line here.
Yeah, is that not true? Is that always true?
It's not always true because it's different times. So if you knew that everything stays sort of like here, one inside the other, then it's true. But U of xt has different behavior in T1 and T2. So in general, you cannot compare.
Okay.
Can I give you just an example, which is a typical example, easy example of fattening. Example of fattening. If I start from this set here, for example. Now what I have that E minus of T is this one. That's E minus of T. In general, for many kernels, I don't want to say for all kernels. And this is E minus of T. And this is typically E plus of T. For example, for mean curvature flow, this is the case, but it's the case also for the fractional mean curvature flow. And so you see, so all the E plus of T always contain all the E minus of T, but never the other way. It's always E plus of T is always bigger of all the E minus of T. So that's the typical example. And what happens to the function u? U develops a flat part, which is all this area here. All this area here is a flat part which grows in time. And you can never compare, you can never put a plus inside some minus. Okay. So now let me just go to the second case I also wanted to briefly discuss, which is the mean convex case. So which means E is such that hk of x greater or equal than delta for all x. It's delta mean convex. Delta greater or equal than 0. And now, in this specific case, what we can prove, in fact, what we were able to prove is the following theorem, that we have two cases, that so now let me just define, let me just give first the definition. Definition that E is strongly delta mean convex if not only E is mean convex, but also the enlarged set of E if E eta, which is the x such that the distance from x to E is less than or equal than eta. So you take some enlarged set, is satisfies hk greater or equal than delta for all eta small enough. Which means that if I have a set E, I can take all my fibrate, I can fibrate a little bit with enlarged set E. This one is E eta. So this condition is a little stronger. It says that if not only E satisfies that, but also the enlarged set, just a moment. And then as a remark, if A is smooth, plus hk greater than delta, then E is, by perturbation, if E is smooth, when I pass to E eta, then the mean curvature changes only a little bit because the integral has only a small variation. So is delta prime strongly mean convex for every delta prime in 0 delta. Now, the result here is that, so in particular, this class it coincides with mean convex sets if we have strictly mean convex set if the boundary is smooth. And so the result here, the theorem is that the same is true, similar thing is true, that E of t, that okay, that if E is delta strongly mean convex, then E plus of T1 is contained in E minus of T2 for all T1 greater than T2. So there is again this property that the evolution is always contained, and E plus minus of T are delta, they maintain the same inequality. They maintain the same inequality, delta strongly mean convex for all t greater than 0. And okay, what is not completely clear here is that so okay, as a consequence, u, the function u, since every level set is one inside the other, for almost every time the two things coincide. So for almost every time, so maybe this I can put as second line. For almost every time. In fact, for every time out of a countable set, we have that E plus of t equal E minus of t closed out of a countable set of times. And of course, here there is a question which we don't know, but I think it's always true, and it's true for the usual mean curvature, that E plus of t is equal E minus of t for all t. It's not so maybe relevant, but essentially that you never have jumps of your function u, but in any case, for almost every time, the function u of t is okay. And then okay, we have some the same as a final remark. Maybe then I can the final remark. The same similar. What is also true is that if E of t is constructed is a solution by minimizing movements, also then E of t is also, or every solution. But now essentially we have uniqueness here, because for almost every time there is only one solution. So the solution here is essentially the same, is also delta mean convex. Okay, that's almost immediate. Just a final remark, then I want to conclude with an example. So for convex set, convexity is preserves, and there is no fattening, everything coincides, E plus, E minus. For strongly mean convex sets, which is not mean convex only, it's mean convex with a little fibration outside, of mean convex set. The same is true. This class is preserved by the evolution, and E plus equal E minus up potentially like a countable set of times, which of course, if we knew that the volume is continuous, for example, which was a question posed before, then probably you can show that this set of strange time does not exist. But for the moment, there could be a set of times where you have little jumps. But there is an example for which that essentially strong mean convexity is needed. Because if you take, okay, for C11 is the same, for smooth is the same. The two notions coincide, but for non-smooth, strong, you can take this simple example in R2, and you take the distance such that here you have a cross. Let's say a cross with 90 degrees. And then you take as a set what is inside here. So this set has a singular point, in the conical singular point, but it satisfies, for example, here it satisfies that HK HK greater than delta greater than 0. This is true for all kernels. for all kernels positive, let's say, in particular for the kernel of the fractional perimeter. So this object is, of course, the delta depends on K, yeah? Delta depends on the kernel. So in particular, this set is mean convex with a positive constant, but the evolution, for at least for K, which is the one given by the fractional mean curvature, the fractional kernel, it develops fattening. So it's not true that E plus goes inside, but E plus goes outside in a similar way as the example of the big cross I was doing before. So what happens is, in fact, that if I have this set, that's a, let me just generically say how is E plus, E minus. This one is E minus, and E plus is something like, you see, E plus goes outside because here there is a problem. And E plus goes outside, and once it goes outside, it never goes, well, at least for some time it stays outside, so you don't have this vibration anymore. There is fattening immediately, non-uniqueness immediately at time 0, so it's a bad initial datum, even if it's satisfied with K. And then I will conclude as a remark, this does not happen for smooth initial data, as I said, but also as a remark, it does not happen for, well, let me write it here, because then I conclude. As a remark, doesn't happen if the kernel is in L1. Because essentially, if the kernel is in L1, it's not important that the set is smooth, because the kernel is good enough that every set is fine. For that kernel, every set is smooth in some sense. Every set is fine. And so as soon as I have positive mean curvature, then if I move it a little bit outside, the mean curvature is continuous, stays positive. So in this example, you don't have E plus. In this example, if the kernel is in L1, you just pick up only the red thing inside. You don't pick up the orange thing outside. But for more general kernels, and there is one important, which is a fractional kernel, this example goes a little outside. Now I want to conclude just by saying what one would like to, okay, we just identified two reasonably simple stable classes, convex sets in some cases, and mean convex sets in more general cases, I would say. But of course, what is still missing is the behavior of the solution. For example, what happens if I let the time runs? Does the set becomes more similar to a ball, to a union of ball? Which type of singularity appear? That's the analysis which has been done more for the mean curvature flow, and essentially is not developed for these more general non-local flows. But we were just concentrating on this more basic sort of properties classes. Okay, so thank you very much for your attention, and I think I can.
Thank you very much.
Thanks.
Questions?
Questions, please.
Where's the chat? Yeah, how does this work?
So, Nicholas, do you have a question?
Yes. My first question is, so we have these stable classes in which also sort of comparison principle is known. What is known for the viscosity solution of the level set equation for general initial datum? Is there a comparison principle proved, or is it false, or what is the situation?
So you're asking for a general kernel?
No, for like, say a kernel L1, like in your assumption with a general initial datum, so not associated with a convex or a mean convex set.
Yes, yes. The viscosity theory has been, I would say, developed in a satisfactory way, in the sense that for all these equations, for all this kernel, under the three assumptions only I was mentioning, there is a comparison principle at the level of the solution U, the function, and the existence and uniqueness of a solution, continuous solution. And this is done, I think it's a nice generalization, and is done in this paper by Chambol, Morini, Ponsiglione.
Okay.
So there is comparison and existence and uniqueness.
And a second question, is anything known about if I take these non-local kernels and scale them in a way such that the Fourier transform would approximate the Fourier transform of Laplacian, that the converged solutions converge to the standard mean curvature flow?
Yes, there is something, let me say, if you take some kernel which decays fast enough at infinity, so if you also add the assumption that k, if I think it's something like that, if the integral, now the origin here is not very important, so let's say, I would say, if so this means that at infinity you don't want, not only integrate k, you integrate a little more, because modulus of x times k, and then you scale by k, for example, k epsilon of x, and now here you have to scale properly, and I think it's like eps, if I don't remember, k of x divided by epsilon, something like that. I don't know if I'm answering. Let's see if I'm answering your question. And then you consider the equation V equal, then you can consider either the energy pk epsilon. This goes from a constant which depends on k, ck, the usual perimeter. That's the usual, the classical perimeter, and also V equal hk epsilon. This goes in the sense of viscosity solution, so uniform, in the sense that solution go uniformly to the limit solution as epsilon to 0. To V equal, no, sorry, the kernel is not isotropic here. So what you get here is not this. What you get here is phi k, where this is some sort of an isotropic perimeter where the anisotropy depends on the k. And here I think up to a constant, you go to something, the curvature dependent I think on phi k.
So that kind of would cover these very old results of Presutti, De Masi, Orlandi, Triolo, Katsoulakis, Oganidis with a smooth kernel.
Yeah, it extends. Yeah, and also there was some related work by, maybe motivated by that, by Alberti Bellettini on the Alencane. Yeah. In fact, in the spirit, this was already sort of studied in this statistical physics literature of interaction, non-local interactions. Yes. But this was in this form. In fact, in this form, it was done. This was done by a student in Pisa, Valerio Pagliari. But basically, he looked into that papers, in fact, and extended and followed the similar approach. And this also was done by him. Okay. And this also was in collaboration. So it's okay, let me see. Okay. Okay. So Pagliari, yes, was a PhD student in Pisa. And now he's in Vienna, with this group. So yes, if it's okay. This does not work. Then it does not work for the fractional perimeter, because the fractional perimeter is invariant by rescaling. So it does not satisfy this condition. is invariant by the scale. So if you just scale it, you just pick up the fractional. You never go out of the fractional mean curvature. It's like for the mean curvature, it's invariant, scale invariant. It does not concentrate somehow. Okay.
Okay, thank you.
More questions? We have something in the chat, not questions. Okay, if not, let's thank the speaker again, and let's postpone further discussion to the informal coffee break. Thank you very much.
Thank you, Matteo.